Lecture 8, Geology 2017. This lecture is continuing our discussion on mid-oceanic ridges. So we have seen in the previous lecture some examples of hotspot-related magmatism, and in the last part of that lecture we were discussing Iceland and some of the relationships of the Atlantic rift and its evolution with the formation of Iceland. Today we continue this discussion and look at different aspects of rift systems. So we will discuss the tectonic environment, so the type of rifts and relative morphology of rift systems more in detail, especially the internal structure, and then look at the composition of oceanic crust in these settings more in detail, as well as talking about the concept of ophiolites, so describe ophiolites, define ophiolites, and give, of course, some examples of ophiolites, especially here in Canada. We'll see some example of Newfoundland. Some other discussion will include aspects such as tectonic settings, again, the spreading velocity, which is different across different rift systems, and then some information on the mantle composition and partial melting and metasomatization. Okay, so if you remember from one of the earlier slides, we presented different tectonic settings and also discussed the difference in terms of annual production of magmas in oceanic rifts versus subduction related magmatism and hotspots. So we highlighted three major environments. With this diagram we are extending our understanding of the complexity of tectonic settings that exist on planet Earth, and we introduce some new terminology. In particular, we talk about different basins where we accumulate sediments, especially in a setting that is subduction related. So very often when we have a subduction zone, like this example with some volcanism, often the volcanism will occur in a back arc setting. So the back arc is usually on the side of the arc where the subductive plate is located. The forearc instead usually is where the accretionary prism forms. So you have an example here of accretion on these other subduction area. So this is your accretionary prism, and so this will be your forearc basin here, and then you have the back arc setting on this other side. In this case we are looking at a continental subduction, so a bit like the Andes, so it's a little bit more complex. You have more thicker volcanism with a lot of partial melting, so you get a thicker crust because of this process of accretion, and also the thickness is favoring the formation of this accretionary prism in this forearc setting. So remember, we have back arc, forearc depending on the location with respect to the arc, and also we have other cases in which we talk about remanent arcs. So many times we form an arc, but then this arc will be moved away, and so the Hawaiian example should now resonate in your mind. So we talked about the fact that a volcanic island progressively over time will lose the magma supply, and so you get essentially a remanent arc setting, which usually gets eroded and become a submarine volcano. So that's the example here of course, through spreading, this will move over time until it finds a subduction zone. Other things, I think you have a set of basins here in the continental setting that is worth mentioning. So we have intra-arc basin settings, we have back-arc basin settings, and again the fore-arc settings. So all these are areas where erosion and weathering will deposit progressively a certain amount of sediment, which then gets consolidated and will form different types of sedimentary rocks. On the top part, you still have the same type of consideration. So we remember that there is roughly a factor of 10 between magmatism that is associated with divergent margins and also convergent margins and other types of basically intraplate tectonics that quite often have a less volume of magma produced. So like this intraplate setting in continental cases, and this would be in oceanic examples. So out of these slides, I think the new content is really this idea of back arc and fore arc. And remember that the fore arc will be always between the subduction zone and the island arc. Good. If we are sort of looking at the distribution of mid-oceanic ridges across the planet, it is quite instructive to look at this beautiful map that shows the continents and the location of the major rift systems on our planet. So starting from the left, you have here the Pacific ridge, and also the subdivisions here on the Cocos, the Nazca, and also the Antarctic plates. So these are subplates separated by other ridge systems. One of them will run down south and cross, the area of the Patagonia and the southern part of South America, essentially, and touch Antarctica, and will run pretty much along the coast of Antarctica, although it's quite far from the coast, but yeah, in line with the coast, and then move up until you find the triple junction here, and you get sort of the rift system that is in the Indian Ocean. So that's quite important as well, which sort of goes up and essentially goes through the Red Sea, and then will connect with all this area of collision that we have between the African plate and Eurasian plate, and then we find the Atlantic rift. If you look at the colors here, we have age of crust, so age of oceanic crust. We discussed this concept already, so you should know that you have sort of a symmetric spread of basaltic crust away from the, for example, the Atlantic rift. But yeah, striking is the fact that you have differential velocity across the Atlantic and the Pacific. Again, this has been attributed to, rather than an increase in supply of magma, it's more an effect of pull of the plate that is through the extent of the subduction domain. So you have here the Aleutianian subduction zone, so quite a bit of subduction takes place in the Ring of Fire, and on this side we are still in the Pacific. Here you can see all the other subduction zones that form the Ring of Fire, and these are all quite important in controlling and regulating the velocity of consumption of crust, and this is essentially a pooling process that will increase the expansion basically of the mid-oceanic rift. So we have that 20 million years go really far in the Pacific, and instead here, as well as in the Atlantic, this process is a little bit slower, and you also in these other rifts as well, we find a similar scenario in which the velocity is definitely the slowest if compared to the other rifts. So that's giving you sort of an overview of the different crustal growth. So crustal growth on our planet is governed by a number of factors, but what is thought is that the subduction zones and their extent are quite important in regulating the velocity of spreading. And why is that? I mean, we have different types of rifts, so you will find that a faster rift usually has a different structure if compared to a slower rift. So we have identified the different velocities on these different mid-oceanic ridge segments. This has also implication for the structure itself of the rift. In essence, usually a ridge that is like the Pacific ridge will be smoother, so you will have less offsets on the fault scarps, and also quite often you have relatively regular magmatism taking place, so it's more continuous. This is linked to the dynamic of the process. Of course, if you have a higher velocity, you need more magma supply. Other things I think are the fact that the Rift Valley is poorly developed, and this is because since you have a continuous feeding of magma, you tend to have an uplift in the central zone, so you don't really form calderas, which are more typical of a slow spreading ridge center. So if you look at the picture down here, you see the difference. There are bigger fault scarps, and you get two major shoulders forming on the rift, which is usually also larger in size, so it goes up to 20 kilometers. So you have pronounced axial valleys, and also, yeah, it's more flat, so you don't have a lot of magma pushing, so it will stay quite flat and form this graben structure, which is common in mature rift systems. So here you expect to have more paucity in the magmatism, so there will be phases in which you have eruptions, others in which it's more quiet, and this is making the whole process sort of fitting with the fact that this is a slow spreading ridge. Further to this, we can look at the morphology of the magmatism. Usually the faster spreading centers like the East Pacific rise has a thermal structure that is warmer, and the crust will be thicker at the axis. Instead, the lithosphere usually is thinner. Higher degrees of melting, so you have usually a larger mash of crystals and magma, and so you have sustained magma chambers and volcanism, as I was stating earlier. And this has also less compositional diversity, mostly because we are dealing with mostly magma supply from the mantle. So nothing really to worry about in terms of major partial melting taking place. Slow spreading have instead a mash that is diverse. You have sort of less fluidity, it's more viscous, and it's also smaller, so the mash itself in the center part. So you end up having sort of a thicker sort of chunk of crust on top of the mash, and yeah, the thermal structure usually is cooler. The crust is thinner at the axis, so by this they're suggesting basically that here the thickness will be much more in total, because you are considering that you have an uplift in the central part. But here, it's thicker from the mash upward, but the overall thickness will be lower if compared to this other example, because you have a depression, a caldera structure that forms in association with this rifting. And so you get a thinner crust in total. So lower degrees of melting. As I said, the volume of the mash will be lower and the volcanism will be episodic, and you have, because of that, higher compositional diversity, because in some cases you have less magma interacting and producing volcanic rocks, and in other cases there will be higher magma supply because of this episodic volcanism. Hence the diversity in volcanic products. If we look at the structure of a mid-oceanic ridge, we will find dominantly basalts forming. So this is because we have essentially at the level of the moho that we start developing this central magmatic chamber in the mantle, and start essentially a factory that produces quite a bit of gabbro on top of a peridotite layer, which is an olivinic layer. So you can think of these green crystals as olivine that is crystallizing. So since you have a spreading center, these subdivisions are extended laterally with progressively cooling down of the magma chamber. You start to develop the gabbro, and then the gabbro will move away together with this initial layer of peridotite. On the side of the subaerial condition, usually you start by developing a layer of basalts, and these are sort of fractured extensively with polygonal prisms that form in response to the interaction with seawater. And so the oceanic crust in this case will be dominated by gabbros and sheeted dikes. On top of that, you form the pillow lavas. So at the summit of the ridge, quite often you will have these massive flows that becomes pillows in response to the interaction with seawater. So there are particular types of structures that you will be able to recognize. There are dikes that are extremely continuous, and then other cases in which you have subsequent intrusions of dikes that will cause a higher degree of complexity. So that's what is illustrated in here. Here you have sort of different phases. So you start with a hot mantle with rock rising and decompressing and melting, and a mash of crystals of basaltic magma. Then a thin dike will erupt and spill lava on the ocean floor, and this produces those characteristic pillows. When the mash cools, dikes intrude dikes to form sheeted dikes. So this is the process of sort of having overprinting of multiple dikes and sort of leading to these columnar structures, which are quite characteristic. Sediments are deposited on the spreading seafloor, so there will be sediments also that culminate this stratification of a mid-oceanic ridge. And yes, the number 5, a gabbro layer is formed adjacent to the magma chamber. I explained that already. So you do have this phase in which the spreading center will crystallize the gabbros. Important to state that in the magma chamber, crystals will settle out of the magma, forming this peridotite layer. So the green layer is dominated by peridotites, which are the result of the fractionation. So if you fractionate stuff at the bottom, usually it's more mafic, and so you increase the amount of olivine, and as a consequence of that you get to a peridotitic composition, which could be dunitic, for example, so dunites will form. So now that we have examined the components of the common components of mid-oceanic ridge, we can look at some of the earlier models and compare them to present-day models for this type of tectonic setting. The majority of the magmas that were sort of represented in this diagram were a primitive melt of variable composition, but mostly morb style, so mid-ocean ridge basalts. So tholeiites are the dominant product, and they are sort of produced by fractional crystallization within the magmatic chamber itself. So we have periodic reinjection from the bottom here of a primitive morb. So you could think of a picritic composition, for example. And then you have dikes upward that extend through the roof of the magmatic chamber and would form this sort of complex of structures, folds, and associated dikes. Crystallization at the top and on the sides is represented by this differentiated melt. And instead, we do develop essentially successive layers of gabbro. And yeah, the model sort of inferred that you had onion-like geometries forming, in which you have different levels of crystallized magma. Dense olivine and pyroxene crystals at the bottom forming these cumulates were also postulated as part of the model, as we have seen in the previous representation. In reality, the modern representation, so this is mid-90s representation of the style of magmatism in a mid-oceanic ridge, and recent seismic work has sort of failed to detect the large magmatic chamber that was illustrated in that earlier model we were just looking at. So instead here you have at least 3 distinct units in the mantle, and also partly in the lithosphere, and these form this set of magmatic assemblages that are representative of a variety of processes that are taking place, but mostly supply of what we could call a normal mid-ocean ridge basalt, and this will be forming our magmatic chamber, but this magmatic chamber is represented by a mash, which is a mixture of magma and crystals, and also you have a pocket of melt which is much more reduced in scale. So rather than having a melt that is distributed widely, we have a situation in which the melt is concentrated at the top of the marsh. So this explains some of the results that are illustrated in seismic studies, which advocate that the layer of fluid magma is quite thin, on the order of a few kilometers. So actually it's on the order of tens to hundreds of meters, so it would be relatively narrow, so less than 2 kilometers wide, commonly between 1 and 2 k's. So the magma chamber will be essentially equivalent to a combination of melt plus this marsh zone, and then if you move out, you enter in what is termed as the transition zone. And this is solid, it's a mixture of crystallized gabbros and magma. So it's transition because of that, because you have a combination of small pockets of melt together with the gabbros. So those are critical differences really in the amount of melt that seems much more restricted and concentrated on the top part. But also we have a complexity that is added by a different type of tholeiitic basalts, and these are called EMORB, so enriched basalts, and usually these are enriched in incompatible elements. By incompatible elements, we mean elements that do not really like to sit in the structure of silicates, so they will tend to get enriched in the highly fractionated part of a magma. So that's a possibility. We might have different degrees of fractionation, so external sort of sources could come into play, and they might be related to earlier volcanic or intrusive phases that were particularly fractionated. So some authors explain these EMORBs as essentially being a recycling of differentiated crust that would be particularly alkaline. So we remember that tholeiitic basalts quite commonly are subalkaline, and so the fact that we find a significant amount of potassium could be an indication of this type of recycling. In other examples, rather, we appeal to lower or deeper sources for the potassium and volatiles, as we have seen already for the kimberlites. And so these sources would be related to pre-existing fragments of crust that were essentially subducted and are floating at the interface between the outer core and the mantle. So this would lead, to those excessively potassic compositions, which could be partly explaining some of these anomalous concentrations in incompatible elements. One example is potassium, one could be barium, and other trace elements, such as uranium, for example. Okay, I think the rest is very similar. So we have the mantle here, so remember those dunites and gabbros, and then the sheeted dike complexes and a series of pillow ridges that develop on top and intermixed with sediment. The Atlantic Reef is different. It is a slow spreading rift. As such, we have a much more restricted mash, and the marshy zone is more a dike-like feature. So the magma is like a vertical body that is pretty much homogeneous. It's again much smaller in scale, and you get, because of that, sort of thicker sequence of dikes on top, and quite commonly the transition zone is also more restricted. So the most of the body will be below the liquidus temperature, so the convection and mixing is far less likely if compared to the fast ridges of, for example, of the Pacific Ocean. So that's a key difference, and remember, we form a more significant rift valley, and also often we have calderas associated with this type of rifts. In terms of geophysical data, so if you look at seismic interpretation, seismic is a geophysical method that uses the measurement of velocity of different types of acoustic waves. So we have the P and S waves, and so in this diagram we have the velocity of the P waves and depth, and we can see how this velocity sharply changes between different parts of our planet, and in a setting like this, which we have different stratifications related to the different composition of the magma that is crystallizing during spreading, we tend to record a sharp variation in the velocity of pressure waves. So P usually stands for pressure, and the other type are S waves, which are shear waves. So in this case, the velocity jumps really when we go from water to rocks. Usually the velocity will increase with density, and this is a good confirmation of what we see in this diagram, because it's essentially growing progressively with depth. And as you see, we have different layers, so we go from sediment in here to extrusives, so the pillows, and then the dikes, and then gabbros, and then we hit the mow. So we have a jump related to the fact that we step into the mantle peridotites. So that's a good sort of comparison with what we find in the field, and it's a good validation of the existence of this stratification in mid-ocean ridges, which makes them quite interesting to study from a geological point of view. So the oceanic crust and upper mantle crust structure considers then 4 layers distinguished based on the seismic velocities. They do not always match with the petrological differences that we observe, but these are important subdivisions that were also validated through other media. For example, deep sea drilling programs helped with the recovery of samples of rock at different depths that provide further information about the change in density, for example. Further work has considered the dredging of fracture zones on scarps, and also the study of ophiolites, which are essentially fragments of mid-oceanic ridges that are abducted on top of an orogen. So when we have thrusting in a big orogeny, we can actually bring up a significant amount of oceanic crust. and this will result in the ophiolites. So ophiolites are nothing less than chunks of stratigraphy of mid-oceanic ridges. So they manifest themselves in a form that is quite unique, and they will have a lot of evidences of the past history of spreading associated with them. So here is a slide of a typical ophiolite complex. This is the SEISMIC ophiolite in Oman, and essentially, as I was stating, the ophiolite is represented by oceanic crust that has been transported and preserved on the edge of a continent. So if you have a continental margin, you have collision, and you can scrape off chunks of oceanic crust that will end up being abducted on top of continental crust, for example, in an erosion. It is commonly incorporated because of that in mountain belts, and this leads, of course, to exposure through erosion and weathering. So for the SEISMIC ophiolite, you have an image here that illustrates the different components. I will not sort of go through the components that I have already illustrated. I would say that you have specific details here that are quite interesting. For example, you start to see a combination or a variety of rocks of ultramafic composition. So we will learn in future lectures that we tend to enrich during magmatism in the upper mantle. We have sort of partial melting that takes place of the mantle, and this will enrich the magmas in particular elements. So for example, chromium could be concentrated in pods, and we might form verlites, which are rocks that have an increase in plagioclase and also pyroxene, and so we lose the olivine, which is actually being captured by restitic rocks such as Habsburgites and Dunites. Other things, you can see this diappear, so you straight away understand that a change in composition will lead to a change in density. So you have dikes that develop, and so you form a diapperism associated with this verlite pod. And this will sort of influence also the structure we observe. So we have, layered gabbros that quite often are found down in the upper mantle. So you have situations in which gabbro is really dominant, and it starts to be part of the lithosphere as well. So you start to form these gabbros down here and bring them up, and these are also linked to the major magmatic chamber that was crystallizing a lot of gabbros. So we have layered gabbros, foliated gabbros, and isotropic gabbros, and this will depend on where they are formed, at which level in the magmatic chamber, and also there are cases of relatively felsic intrusives found as outliers in this context. One example are these plagiogranites. And the other stuff is very similar to what we discussed, so I'm not going to spend additional time on that. In this image, you have a summary of some of the key structures that are found in the field, and they are linked with letters to the different parts of the mid-oceanic sequence, or the ophiolitic sequence that has been sort of examined and dissected by Dillek and Ferns. The figure you see here on the slide are illustrated a series of important structures and discontinuity, as well as modal mineralogy changes. So we can start from the bottom. In A and B we have what are defined as upper mantle rocks, and these will be your Habsburgites and Dunites, and they are restitic rocks that often get deformed, so you can see examples of folding in here, as well as some of the modal mineralogy variations. So we have some subhorizontal veining in this case, which is likely represented by plagioclase. So calcium-rich feldspar will be abundant in these rock varieties. These are fairly compact and they do not really show big compositional changes like the figure C. In this case, you can see a clear switch between a greenish, light greenish color and dark gray colors, which form a zebra pattern that is characteristic of layered ultramafic rocks. So these rocks are usually representative of the transition into the MO, which is the Morovicic discontinuity between the mantle and the crust. So this separation is quite important, and it's also important to remember that it's not strictly matched by the separation observed in the seismic velocities. Besides this, we have also a number of other things that occur, and we have sort of a transition in composition between these layer ultramafic rocks that progressively become less enriched in magnesium, and so they will get more pyroxene as well as more plagioclase, and in response to that they become layer gabbros. So this is roughly a thickness of a kilometer until you get in more various or varitexture and isotropic gabbros. So you have some images of these gabbros in E. So varitexture gabbros will not display this classic stratification, which is typical of the layer gabbros. Other important aspects are the transition between these gabbros, so the varitexture gabbros, and the sheeted dike complex, which is more dominated by basaltic compositions. So in this particular case, this is a quite irregular boundary, but it can be identified by looking at, for example, figure G, in which we have the sheeted dike complex, and often the margin will be quite irregular, and you see clearly a change in composition. In this case, often you have that the gabbro will be cut by basaltic and felsic intrusions. If the felsic intrusions are forming, usually you term them plagiogranites, and alternatively at the end of the phase of magmatism we often have boninites that are cross-cutting all the ophiolitic sequence and will deposit as a final stage of magmatism. This usually intersects also layer 2A, which is represented by lava that progressively get more felsic in composition. So you start with mafic lavas that are pillow lavas. You can see them in E. So I here will be dominated by these pillows. You can see irregular pillows forming and touching themselves in contact with an irregular geometry. And then we have under H these volcanic breccias, and that's because often you have these normal structures that develop that will contribute to the fragmentation of the pillow lavas and other volcanic material. In J and K we have indications of changing composition. So we go from these mafic lavas that are dominated by basalts into more cherty lavas or quartz-rich lavas, which are andesitic composition as well as more felsic composition, such as dacites and rhyolites. And yes, J and K are good representations, but K it's more of a chert, which is actually a later stage of sedimentation that will be independent of the magmatism or partly independent, because it does include a significant amount of clasts that are independent of the formation of the rift. So they are non-magmatic. If we take an example of a Canadian example, we can mention the ophiolite sequences that are found in Newfoundland, so in eastern Canada. We have essentially two major sites where ophiolites are recorded, and these are the Bay of Islands example and also the Bats Cove examples and Mings Peak examples in here, as well as the R Bay up here. The two major sites are really this Baia Verte ophiolite belt and Bats Cove, as well as the Bay of Islands. These are of variable age, but mostly Ordovician and Devonian ophiolite complexes. And here you have a view of the Rocky Gulch in Lewis Hills that essentially provides a good representation of the alteration that takes place in these ophiolitic complexes. So the reddish color is clearly an oxidation of some of the ultramafic rocks. If we focus on the Bay of Islands ophiolite complex, you can see here a geological map that represents the different units that constitute the complex. These are highlighted in orange. So if we walk from northeast in this direction, so toward northwest, we will start at the base of the ophiolitic complex, finding a metamorphic soil. So if you remember, when we talked about the origin of ophiolites, we mentioned that these are abducted, so they are transported on top of continental crust, and this continental crust may be subject to orogenies, so you are in a situation in which you are in a subduction zone, so you start a thickening crust through deformation, and this deformation is often accompanied with metamorphism. So metamorphism will consider these sort of base of the ophiolitic sequence leading to a sharp difference because these rocks will be highly deformed and metamorphosed, and then you have on top a series of ultramafic rocks which would represent a chunk of the upper mantle essentially. After this you get the gabbros, your mafic dikes, and then the pillow lava. So if we walk in this direction you realize you can see the different formations we are mentioning, and these are concordant sequences that do reflect the products of a large magmatic chamber or magmatic complex, which is often associated with the mid-oceanic ridges. So this is a good example. So these are the Lewis Hills here, so the previous photographs, and so there are all these hills with these characteristic stratigraphy that are quite interesting to visit. In this other example you have a contact, this is a sheared set of ultramafic rocks at the base of the ophiolites that were deformed during transport of the oceanic crust onto the edge of the continent. In this case is the Laurentian continent or Laurentian plate, and it is essentially part of the Bay of Island ophiolite complex. So you can see here slices of ultramafic rocks that are basically forming these slivers that are thrusted onto a metamorphic soil. Often the importance of ultramafic rocks has economic importance. If we think of the composition, often these rocks will be extremely rich in iron and magnesium, and the magnesium in particular tend to react and serpentinize, so you form serpentine minerals which are quite soapy, as mentioned earlier when we were discussing some of the characteristics of serpentine. So serpentine can be used for the production of a variety of items. If you think of countertops in a kitchen, in the past they've been constructed using this stone, but yeah, the history of this stone is very ancient. Even Egyptians used to build artifacts with the soapstone. One example could be ornaments. So for example, the jewelry that Egyptians used was partly made with soapstone. A good representation often related to their gods was the construction of scarabs that were made of soapstone. It's also important for the history of North America. If we think at the Inuit tribes, they used to construct oil lamps based on soapstone, as well as other things such as bowls and pretty much all sort of utensils, really. And yes, and this is famous also for Newfoundland with this bowl factory in Dorset, which is one of the oldest, I think, for the production of soapstones. So it's dated 500 before Christ. If you look at the characteristics of the ophiolitic sequences, we have essentially different layers, at least 4 distinct layers as we have seen, but some under subdivisions are also considered. and this is based on some of the petrological characteristics that we have just illustrated with that cross sections from DLEC. I would say that if we go in order, the layer 1, it's a thin layer of pelagic sediments. By pelagic, it's meant that is essentially composed dominantly by organisms that precipitate when they die on the bottom of the ocean. They will produce accumulations that become sediment. There will be also minor clastic supplies as well, depending on how far you are from a continent. Typically, the ophiolite in layer 1 will be relatively thin, less than a kilometer. Average is 500 meters up to a kilometer, and you can see here the relatively low velocity, which are less than 2 kilometers per second for the pressure waves. Progressively, these values will jump while we move into the basaltic complex, so the sheeted dike complex, and we'll see that if we look at the vertical sheeted dikes, we have a set of pillow lavas as mentioned, and the more clear sheeted dike complex, so vertical dikes and placed in shallow brittle extensional environments. And yes, many dikes have these characteristics of showing only a single shear margin. Instead, later dikes will split and intrude the earlier dikes. In this particular case, the thickness of the layer 2A, B, and C will be mostly on the order of 2 kilometers, with essentially basaltic pillows roughly having an average thickness of 500 meters. The velocities have a big jump in these pillow lavas. They go from 2 up to 5.6, and then they even go closer to 7 for the sheeted dike complex. Some examples here of pillows. So these are modern and ancient pillow basalts. We have seen plenty of these images for the Hawaiian volcanoes, but this is a slightly different context. So we will have clear evidence of these pillows because of the growth of the pillows and the fact that they are essentially quenching and so forming yellow clastites quite commonly. Some examples here of a mid-oceanic ridge basalt. This is a thin section that is showing some of the minerals with a very high magnification, and also this is a particular image because it does have crossed nickels, so we are looking at characteristic interference colors for the minerals. So these elongated minerals, you should recognize some of the twinning, which is typical of the plagioclase. So this will be phenocrysts of plagioclase. Then we have olivine phenocrysts, which are more rusty in color, more reddish, and usually do not show any significant cleavage or twinning. So that's a big difference. And here, if the minerals have a purple color, quite often they are pyroxene. So they will show a classic 90-degree cleavage, and everything, all these phenocrysts are included within a microcrystalline matrix. So you can see, because of the high magnification, what microcrystalline means. It's essentially a repetition of the phenocrysts at a smaller scale. So very tiny crystals of plagioclase are visible, as well as some of the pyroxenes because of the high interference colors. so in purple and blue in particular. If we move on and we look at the gabbros, remember that we have this change from layered versus more various compositions and textures at the top, which will be more irregular. And yes, the layering can be horizontal, but more commonly can dip at higher angles as well, up to 90 degrees. Clearly the velocity is getting higher because of the increasing density, so the P waves are up to 7.1 and the thicknesses are slightly higher, so we are on the average of 4.7 kilometers in average. Typically they go from 2 to 5. Discontinuous diorite and tonalite bodies will occur, so the plagio-granite or tonalite, we mentioned it, it's essentially a highly fractionated magma that will intrude at the interface between the sheeted dike complex and the isotropic and foliated gabbro layer. So at the top of the gabbros you will find the small discontinuous diorite and tonalite bodies, and these are late differentiated liquids that essentially are mobilized along the sheeted dike contact with the gabbros. Sometimes these can extend further up as well. An example of a gabbro here, again in thin section. This time we have a scale, so 2 millimeters. It gives you a good understanding of the size of this crystal, which is slightly more than 2 millimeters. So you have a big magnification in this particular case. So you can see here the abundance of plagioclase. You can recognize some of the twinning as well and some of the cleavage that is characteristic of plagioclase, as well as the presence here of pyroxenes that is quite abundant, and you can see the cleavage clearly. If it would be olivine, it would not really have this type of cleavage. In this case, we are looking at an image that doesn't have crossed nickels, so these are the real translucency related colors of the minerals. There is probably also some amphibole in this gabbro, and also potentially a crystal of olivine in here. So this is a summary of the layer 4, which is representative of the mantle, and I guess the contact really with the mantle and oceanic crust. So upper mantle and oceanic crust pretty much are in contact at this location, petrologically speaking. In this location, commonly you have the bottom of the magmatic chamber, so you tend to have a significant amount of cumulates, and this will include chromatites, gabbros, and also verlite. Verlite is essentially a rock dominated by clinopyroxene. In this case, you have an example here with these green minerals, so deep green minerals, which are the chromium diopsides. So pyroxene will be dominated by this variety. There are also quite a bit of other crystals, but the red ones will be dominated by garnet, and the pistachio green is olivine. So dominantly this rock is represented by olivine and pyroxene. So it's essentially a gabbro with a characteristic abundance of clinopyroxene. Other types of rocks include more restitic rocks, so rocks that has seen quite a bit of partial melting, so the magma separates and go and forms the basalts in the oceanic crust, so the pilobasalts. But what's left usually it's the Habsburgites and also the Dunites. So these rock varieties, which we will see in a second, they are of course texturally distinct, and the abundance of olivine is much more pronounced in these rocks, especially Dunite, which has more than 90%, as we will see. So this part here is essentially the mantle, and so it's going to be dominated by this variety of peridotites, and it will have your 7 kilometers exposed in this particular section. I think this section are part of either the Troodos or semi-ophiolite complexes, which are good examples of these ultramafic assemblages. So if we focus on the rock types, you have here other examples of verlites and lerdulites. Their textures can vary. We have different proportions really of ferromagnesium minerals, but yeah, the pyroxene and olivine will be really dominant. So we have another term that we introduce here, that is the term lerdzolite. A lerdzolite is essentially fertile, unaltered mantle, so it's the rock that we start from. So if you are a chunk of mantle, it will be lerzolitic in composition. So it will be mostly composed of olivine, orthopyroxene, so commonly the enstatite, and also some diopside as well. And it does have really high proportion of basaltic ingredients, which could include garnet and clinopyroxene. So lerdzolite will essentially be melted partially, and the result is that we are losing something from the lerdzolite, and this is going to compose gabbros and basalts in the crust, because it's the sourced magma basically. What is left will be dunites, which are mostly olivine, and Habsburgites, which are a combination of olivine and orthopyroxene. So the orthopyroxene is getting enriched, and you will lose the clinopyroxene that goes into the verlite. So verlite will be composed by olivine plus clinopyroxene, so that diopside that we saw before. You have here some example of the xenolites containing lerdzolite. So sometimes in a magma you get fragments of mantle entrapped, and these are quite commonly xenolites, and these will have a variable composition. So they look like an intrusive rock with well-developed equigranular texture, and the result is commonly a very abundant xenolite, very abundant in olivine. So this is why it's greenish in color. And so this pistachio green is characteristic, and then you have black dots, which will be dominantly pyroxene. And in this case, it will be orthopyroxene and clinopyroxene, so a combination of the two. And in this other case, it will be dominated by clinopyroxene, as mentioned. Lerdzolites are a type of peridotite, which in essence can be represented in this ternary diagram. So if we have olivine at the top, orthopyroxene and clinopyroxene, you can sort of see the different rocks we mentioned in these diagrams. and so the only addition will be these websterites, which have relatively low olivinic content, but they still have quite a bit of olivine, but they will get really dark because of the content in pyroxene that is kicking up significantly, so more than 60% in this particular example. The extreme will be the websterite, which will lose the majority of the olivine, so it's basically a pyroxenite. So we are in the field of pyroxenites here, and this is distinct from the peridotites, which are more of a mixture between pyroxene and olivine. Okay, so the lertholite, it's almost a 50-50, and then you have the extremes of the Habsburgites and Verlites, which will have, as I stated, a different pyroxene composition. So the symmetry of the pyroxene will change based on the substitutions. So for example, chromium-rich pyroxene will be representative of the clinopyroxene. Classic orthopyroxene will be enstatite, which is magnesium-rich. And this is really an indication of also the different fractionation that takes place. So while the magma fractionate and partial melting takes place, you will change the content in pyroxene based on the composition of the rock. So more fractionated varieties will be dominated by orthopyroxene. Instead, relatively primitive magmas will be more clinopyroxene rich. An example here of the fractionation is represented in a ternary diagram, which looks at different temperatures. Sometimes petrologists like to put isolines for temperature and look at the mineral equilibriums. So we can plot things like this, and these are eutectic lines that shows the coexistence of different phases. In this case, for example, we have olivine and plagioclase. So along this line, at a temperature that is around 1300 degrees, we will have a combination of melt and crystals of anorthite and phosterite, basically. So olivine and plagioclase, so a tractolithic composition. When we reach this point at 1270, we have three phases coexisting. So we have diopside, so the pyroxene is coexisting with phosterite and anorthite. And so we enter in a field in which we are basically crystallizing everything that usually composes a peridotite or an ultramafic rocks. Remember this subdivision we mentioned based on the silica content. So all these rocks will have very little silica, and so less than 45% silica oxide. So these are ultra basic rocks, and these usually lead to the formation of dunites and comatites if they are effusive rocks. So of course this diagram has implications also for the sequence of crystallization. So if you are at very high temperature, we tend to form rocks that are exclusively composed of phosterite, so olivinic rocks. And then when we cool down the system, we start to develop more plagioclase and progressively go down to a situation in which we have also the precipitation of clinopyroxene. So clinopyroxene is essentially occurring early in this phase of crystallization, and it will accumulate at the bottom of the magmatic chamber. And so that's why you get these verlites forming. Here is another diagram that tries to explain the relationships that leads to the partial melting and production of tholeiitic basalts. So we are using in this case aluminum, and so a major element versus trace elements like titanium, and these tend to get enriched in a tholeiitic basalt. So we go essentially from a composition that is lerzoleitic into a tholeiitic basalt that is more felsic progressively. And at the same time, we leave restitic rocks that have asburgite or dunite composition, so they are particularly rich in magnesium, basically. So that's how the fractionation increases the amount of trace elements as well as major elements like aluminum. So a mid-oceanic rich basalts will form dominantly by partial melting of the mantle, leaving behind these restitic materials, which are essentially asburgite and dunite. The lertzolite again is the fertile unaltered mantle, and I think this information sort of gives you the feeling of this transition that takes place during partial melting, and explains why we form gabbros and basalts. They are essentially separates and more fractionated magmas that are derived from the mantle composition. And this reconnects with the Bowen sequence lastly. So remember that we had that loss in calcium and progressive increase in aluminum-rich silicates, which would be your alkali feldspars, as well as other minerals, ferromagnesium minerals such as biotite and amphibole, will have quite a bit more aluminum in their structures. If we consider the change in pressure temperature with depth, we can construct a geotherm that illustrates the path that the mantle takes when it separates and forms basaltic magmas. And so, of course, to allow for the production of a liquidus, we need to cross this boundary here, which is a zone that separates the solidus from the liquidus. So, of course, depending on the pressure and temperature condition, we will have different phases. So if we look at the lertzolite composition and also the other rocks, so the verlites and so on, we have that we form high pressure phases and low pressure phases, for example. So it will be more characterized by garnet if we are on the order of 200 kilometers because we have 5 gigapascals at that depth. So as a consequence of that, you tend to have a variety of phases. So at low pressures, you tend to have plagioclase and spinel that will crystallize more easily because they are more stable at lower pressures. So the mantle geotherm is shown in blue. The geotherm represents the increase in temperature of the mantle with increase in depth. As the mantle geotherm lies in this example below the solidus, the mantle does not really melt in this context, but still you have sort of different minerals that will form depending on the conditions or will be present and represent this precursor rock, which is the lertzolite. So here you have a better sort of illustration of the different mineralogy. So we start at more than 400 kilometers with stishovite, which is a high pressure variety of quartz, which will have a coordination of 6 of the silica, which is quite unique and linked with the elevated pressure. After that, between 80 and 400 kilometers, you find the garnet, and then you have the spinel, and ultimately at less than 50 Ks, the plagioclase. So there are 4 types of mantle lerdsolites, and you explain these different types by looking at their pressure temperature condition of crystallization. If we are along an adiabat, so often when we are in a mid-oceanic ridge, we take the mantle at depth that is unusual because of the upwelling related to convection, and this of course let the geotherm becomes shallower and causes melting, because we enter in this area of melting. So the partial melting is expressed by different percentages here depending on the temperature condition, and we call this an adiabat because we have a rapid ascent of the magma with essentially a constant temperature, but a rapid change in pressure or decompression phase essentially. So this decompression will cross this curve and lead to the production of melts. So that's one factor, but certainly then you will have other things like fluids, so fluid separation and the fluids derivation from deep-seated fractures will also contribute to partial melting because of the metasomatic reactions that takes place in mid-oceanic ridges. And of course, this is a style of tectonics that is related to mantle plumes. If you take the example of Iceland, you have a good indication of the effect of a plume and its role in sort of changing the compositions of the morb basalts. Other things, I was talking about the hotspot idea and the intersection with mid-oceanic, with the Atlantic ridge in Iceland. We could look at that in the context of the composition of the mid-oceanic ridge basalts. So in the mid-oceanic ridge, we separate the plates, we form a discontinuity, and we have that the mantle flows upward. I have explained this process as related to convection. But essentially you form an area of mixing where you mix 2 types of mid-ocean ridge basalts dominantly, so the E-morbs and the N-morbs. So this distinction is based on the amount of trace elements. So usually E-morbs will represent an enriched mantle, and we saw that a number of processes can lead to enrichment of mid-ocean ridge basalts in terms of trace elements, as well as some of the major elements such as potassium. So ultrapotassic melts may form because you have exotic chunks of crust that have been transported through subduction zones, or you might have slivers of mantle that contain particularly enriched minerals such as amphiboles that contain quite a bit of potassium, and so they will contribute to these exotic melts. The normal morbs usually have a concentration of potassium that is very low, on the order of a few ppms, and they really have also low trace element concentrations. If you look at the composition of basalts and also gabbros, because they have the same really chemical composition but different textures, and as we have seen, they crystallize in completely different condition, and that's explaining why they do get different structure. But yeah, if we focus on the chemistry, as I was stating, for a morb, usually it's an equivalent to an olivinic basalt with relatively low potassium concentration, so less than 0.2%, and also trace element will be also very low. So similarly, we have titanium that is less than 2% in the rock. So basalts that are forming early will be having olivine, plagioclase, and also calcium-rich pyroxene is quite often the case. So you will have augites or diopside. So we saw the example with the verlites earlier. The matrix of the basalts usually is represented by microscopic clinopyroxene and also plagioclase. And then you have your oxides, so there is a little bit of iron and titanium oxides. It will also not really contain very much K-phosphate, which is expected. So if we focus on the process of crystallization, you can see that you start with really little titanium and little potassium, but progressively we get an enrichment while we fractionate the rock, and this is proportional also with the amount of magnesium, which is something I was mentioning when we transition from ultramafic to mafic assemblages. We lose a lot of magnesium and we gain in terms of silica, but there are other type of losses. We will have also a switch in terms of calcium, so we lose some calcium, and also aluminum is in a decreasing trend because it's fractionated in the feldspars. For other trends, certainly the sodium and silica will go up together with phosphites, and so the phosphate group and also the titanium concentration, as stated earlier, will be in a positive uptrend. So these are all things that will increase in highly fractionated melts. So MORBs are the product of fractional crystallization, melt aggregation, and also interaction with seawater and crustal contamination. So the seawater interaction is obviously related to this kick in the sodium and also potassium. So we do see the effect of interaction with seawater with the increase of these alkaline and calc-alkaline elements. Magnesium contests are a good index for fractional crystallization, as stated. So often the correction is done back to the 8% magnesium oxide. So we go to this composition, and so you essentially revert all the compositions of these other oxides so that you essentially infer the primary melt composition, and that allows you to compare back with other data sets and understand the diversity in the source magmas, basically. If we move on, we can see here that leads us to understanding that the light rarer elements usually prefer to stay in the melt, and this leads to this concept of incompatibility. So I mentioned that trace elements are found in more fractionated rocks. So if you take a primitive composition like a chondrite versus the samples of rock you have and you ratio them, you can essentially see the difference between different suites of magmatic rocks, and this allows you to establish source compositions. So in this sense, Ocean Island basalt, which are the ones we saw for the hotspots, tend to be enriched in these light rarer elements, and because of that they can be differentiated from the morbs, which appear to be relatively low, with the ratios that are on the order of 10. So there is a 10 time or magnitude of 10 or 1 order of magnitude difference between OIB and morbs. Towards the heavier side, you get a situation in which they start to be very similar. So these rare earth elements are less useful to differentiate the two series. So this is suggesting that the morb will derive from a relatively depleted mantle that doesn't really have any enrichment in light rarer elements. Of course, we have to be careful with E-morbs, for example, which will contain exotic amounts of some of these in response to the interaction of the magma with, for example, crustal contamination, so fragments of crust that have been subducted and reach the interface with the outer core. So in conclusion, in this case, so the morb case, we have a depletion. So morbs derive from mantle that is depleted in light rare earth elements. Instead, since the plumes come from deeper in the mantle, we have cases in which we have an enrichment. So they come essentially for a non-depleted enriched mantle, which can be linked to the processes I was mentioning earlier, so contamination from other fragments of crust. So the plume may be of independent but geographically coincidental origin. The enriched plume usually undergoes decompression melting to form these E-morbs. So the lower part of the mantle can be enriched in these light rare earth elements, and yeah, the process is very similar to what we saw for the N-morb. You tend to have a situation in which you have a phase of melting that leads to a transfer of magma at a higher level in the crust. And so as with the N-morb, the melt will not segregate until shallow depths, where the major element and mineralogical character is determined. The morb and N-morb melt blobs can mix to a varying degree, as the result usually is a T-morb, which is essentially the funnel to the ridge. So I was saying that while the E-morb rise from diapirs and it reaches these N-morph zone, so the zone of melting for the normal mid-ocean reef basalts. Okay, we were explaining this process of rise of contaminated mantle that is enriched in light rare earth elements, for example, and other elements such as potassium, which we saw it's quite rare in the basalts. And the melt will rise, form a diapir, and then the diapir will move further and interact with the N-morph components. So this will result in a transitional morph, which is usually found in these funneling sites where we have the ridge, so the main boundary really that separates the two crusts, and this again will be a mixing of these two distinct types of magmas. So there are a variety of situations. This is just to highlight really the complexity of the different type of magmas, and also illustrate where the source of enriched mantle is located, and the role that it plays really in controlling the different composition of these melts. So this is another diagram that again shows a similar concept to what we saw before, was comparing ocean highland basalts versus the mid-oceanic ridge basalts. So in this case you get a perspective of the level of enrichment if comparing the number of elements, so major and also trace elements in this case. And so if we take again the lanthanum, for example, we do see that lanthanum tends to get enriched in the E-morphs if compared to the N-morph. So in the end the story is very similar to what we saw for ocean island basalts, but of course the scale of enrichment is rather different because we are still dealing with a mid-oceanic ridge basalt rather than a magma that is directly sourced from lower levels in the asthenosphere. So we talk about on the order of 400 kilometers for ocean island basalts. Instead, in this case, the magma can be relatively shallow, so on the order of tens of kilometers. So remember here the scale is your sample divided by a primitive sample of the upper mantle, so a sample that could be a larzolite that is undifferentiated, so relatively fresh. There are exceptions to this, and we can see that for these heavier rare earth elements like dysprosium, there is a very minimal difference, but still it does exist, so we can see some difference. These are essentially the samples that were used for the construction of these plots. Ideally, you use essentially volcanic glass that is grabbed off pillows or other volcanic products. This will help with the chemical analysis that then lead to this type of representations. Some other information about the fractionation. So fractionation, one change in computable element ratios. So this is an important concept. If we take two rare earth elements, so lanthanum and samarium, we note that there is a difference in their value, so the ratio will increase when you have enriched morbs, which is expected because we are ratioing a light rare earth with a rather heavy rare earth. And here in this diagram we have the relationship with the magnesium. If you remember, I mentioned that magnesium is essentially higher in ultramafic rocks, so the ultramafic rocks would sit on this side, and on this other side you have more fractionated rocks. And you can see there is not much variation in terms of duration depending on the fractionation of these basalts, which indicate that the enrichment that we observe is rather related to the source rather than being the product of a different degree of fractionation. So when you collect the rocks, even if they are part of a fractionation series and they are more differentiated, this ratio will will be constant. So we have seen that we can use ratios to evaluate the degree of fractionation. Other ratios are commonly considered are based on isotopes. So you take the same element, but you have a different atomic mass because usually an isotope has additional neutrons in its nucleus. And so you can have different weights for the same element. So it does happen that light elements will tend to go in to the either depleted phases or rich phases. So we can see an example here in which we look at neodymium 143 divided by neodymium 144, and also strontium 87 to strontium 86. So in this particular case we have the normal condition of the morb that is clustered here. So they have essentially investigated samples from the Juan de Fuca Ridge, for example, or the Indian Plate, and we can see that we have a condition that is relatively normal with these values of the isotopic ratios. In fact, the samples are all clustering around it, but then we have a linear trend and two extremes. So one is the enriched extreme, which is 2 standard deviation enriched, and this other is instead a suite of samples that are relatively depleted. And so in this particular case we can see how the isotopes are useful actually in the discrimination of different levels of enrichment. Really, the same applies for these lead isotopes. Quite often for this particular isotope is the presence of uranium will condition the abundance of 207 and 206 because they are radiogenic isotopes. So the result will be that when you have a lot of uranium, you tend to grow these values, and so you get a higher ratio. So that will give you these compositions, and so you will be, on the order of 2 sigma enriched when you are in this part, or over when you are in this part of the spectrum of isotopic ratios, so above the 19 and also above the 15.6, let's say, or 55 more correctly. If we look at the stable isotopes, so same concept as before, instead of the radiogenic, which are the product of decay from radiogenic elements, we can consider natural isotopes like helium, for example. It's found with different atomic number So we have helium-3 versus helium-4 in this example, and you can see how we can differentiate ocean island basalts from the morphs. So we can see down here with a ratio roughly of average of 8 or a window that actually goes from 7 to 9. We find this spectrum of morph basalts from the Mariana Trench. So they have pretty much consistent composition in terms of ratio, and here we have slight variation between the Manus and these other back arc basin basalts. So that's kind of a good way of using stable isotopes together here with a percentage of delta 18, which is also the oxygen isotope. So oxygen 18 divided by oxygen 16 is commonly used to represent this ratio, and in this case this is represented as a percentage or per mil more correctly because of the quantities. So certainly both radiogenic and non-radiogenic isotopes will be useful to differentiate the level of enrichment in different magmatic suites. Another way to apply helium isotopes, and so the same ratio as we were seeing that we use to differentiate different types of basalts depending on their source. Well, in this case, they can be used to identify the position of a ridge, and you have here the example from Craig and Lupton that illustrate the East Pacific rise. So we have pretty much this profile of the rise, which is related to the seamounts that form when you are on the ridge. And you got the scale here that gives you the indication of the distance of this covered by this profile, and also on this side you have the depth in kilometers. So if you are sort of able to detect and calculate the ratios of the delta helium-3, you can understand its distribution in seawater. And so what these people realized is that helium-3 actually comes from deep in the mantle, and it's something that is primordial. So it's not really generated by any radiogenic processes. Instead, so it's similar to lead 2O4. Instead, here the helium-4 is the result of a radiogenic process. So it's important to remind you that in the previous slide, the stable isotope was the oxygen, but the diagram combined essentially a radiogenic ratio with the stable isotope ratio. But in this case, we are using just the radiogenic component, and of course, if you have a lot of this primordial helium, it's more likely sourced from deep in the mantle. So the helium anomalies at ridges are evidence of degassing that comes from deeper parts or of the mantle. This is also illustrated here, because if you look at the crustal composition, this ratio will be under 1. Instead, for mid-ocean ridge basalt, it jumps to 8. And on arcs is also very similar, but you can see in the hotspots deeper that contain OIB type basalts, so ocean island basalts will be definitely more enriched with a value of 37, which is consistent with what we find here right on the ridge axis. So very interesting to see that some of these ratios can be used spatially to map out the location of a ridge and to understand also the type of magmas again that we are dealing with. So if we switch back to the for a second on the stable isotopes, we can clearly see the same trend. So we have that the radiogenic helium, which is the number 4, tends to be relatively high in the morbs, and instead in ocean island basalts we tend to have that the helium-3 dominates, and so we get higher ratios. In this final slide, we can complete this lecture by looking at a summary of a series of complex interactions. So we have seen that a lot of the geochemical information that we can derive from the chemical analysis of different types of basalts or gabbros can lead to a number of interpretations. But dominantly we see this trend that differentiate depleted mantle samples from ocean island basalts compositions. And so we saw also that we can have conditions that are mixing of the two components, which lead to the E-morbs or enriched morbs and transitional morbs as well. What does this have in terms of implications for the discrimination of the tectonic settings? I think the critical aspect is that the proportion of enriched OIB will be really the key factor for distinguishing intraplate hotspots. Instead, mid-ocean ridges will have dominantly normal conditions of mid-ocean ridge basalts. So tholeiitic basalts with relatively low potassium content and also relatively low trace elements such as titanium. There will be mixed conditions in which we combine a plume with the morbs, and so we form enriched morbs that mix with normal morbs. So there might be situations in which we have anomalous potassium abundances in the basalts that come off mid-oceanic ridges. However, if we look in terms of volumes, extensive volumes of melts will have these characteristic composition, so there will be depleted mantle compositions. OIB will be found also in seamounts, but this is like a minor process, and also if we look at the subduction environment, we have really here the addition of the enriched melts plus incompatible melts, which are quite unique because they are products that derive from a radiogenic crust that is enriched in uranium. So having signatures of this type that comes from continental crust at depth is a possibility to explain some of these enrichments that we find. So the final concept is the idea of transporting sediment and oceanic lithosphere that then get recycled into the OIB reservoir. So these are really complex processes, and there is still abundant research and which explains why we have plenty of question marks in some of these parts. So there are domains like here that we have no access to, and so it's very hard really to understand in detail the type of processes, but a collection of evidence is supporting the idea that you have these fragments of oceanic crust that contribute to the complexity of these enrichments. So this concludes this lecture. In the next one, we are going to progress with another important tectonic settings, which is the subduction zones. So we will move out of these extensional environments and rather look at compression and different types of subduction related magmatism.